Okay, so this is section 1.8, and we're going to talk about combining functions through addition, subtraction, division, multiplication, and we're also going to talk about our composite functions. So when we're looking at the sum, the difference, products, and quotients of them, again, if we have the sum, I'm literally going to take f of x, add g of x to it. If I have the difference, I'm going to take f and g and combine them. I'm going to combine like terms, take the difference. When I'm multiplying, I may have to FOIL or distribute. And when I'm dividing, I have to consider that I cannot have 0 in the denominator. That's important. When we're doing composite functions, we're literally going to plug in g into f or f into g. Okay, so here's example 1. What we're going to do, we're going to do part A, we're going to add them. Part B, we're going to subtract the two functions, multiply them for part C, and divide them for part D, and we're going to find their domain. Okay, do we agree that the domain of these two functions, f of x and then g of x here, is the set of all real numbers? X is not being restricted, so that's something that I want to look at, evaluate, and think of just off the bat, that the domain of these two, let's write that, the domain for this function is from negative infinity to positive infinity, as well as the domain for this function, negative infinity towards positive infinity. So that way I know I'm not restricting anything from the beginning. The next thing we're going to do is we're going to actually find the addition, the subtraction of these functions. We're going to multiply them, we're going to divide them, and we're also going to take a look at the domain, see if it's affected as we're doing these computations. So let's begin with adding them. Okay, so we're going to begin with adding them. So let's find f plus g of x. So I know f of x is 2x plus 1, and I'm literally going to add g of x, which is x squared. The only thing I can do is put these in descending power, so my answer is x squared plus 2x plus 1. There are no like terms, so this is my final answer. Okay, so that would be the addition of these two functions. Did I restrict the domain here? No, I don't have anything in the denominator of something. I don't have the square root. So the domain here would be from negative infinity to positive infinity. And notice that it's somewhat similar when I subtract them, except the difference is that it's going to be minus x squared. So this is f of x minus g of x. Put it in descending power, our answer is negative x squared plus 2x plus 1. I did not restrict the domain here, so the domain is also from negative infinity to positive infinity. The moment I multiply them, it's also not affected too bad, the domain and range. So f times g of x, where f of x is 2x plus 1, g of x is x squared. I'm going to go ahead and I'm going to distribute x squared to both terms. We're going to get 2x cubed plus x squared. Here we did not restrict the domain either, so the domain of this one is from negative infinity to positive infinity. When we divide, that's when we start restricting a little bit more. I just want to mention that if you're restricted from the beginning, from the given f of x and g of x, you have to incorporate that into the new domain, and in my next example I'm going to show you that. So now we're going to divide. So let's divide f divided by g. F over g of x, where f of x is 2x plus 1, and g of x is x squared. That's simplified. I can't reduce that any further. And we have to think about what is going to make the denominator undefined. 0, right? So I want to exclude that from the domain. So here I have my first restriction for the given function. So from negative infinity to 0, 0 to positive infinity if we're using interval notation. Okay, so here's part B, and we're going to do the same thing in this example. We're going to add them, we're going to subtract them, we're going to multiply them, and we're going to divide them, and we're going to evaluate their domains. But if we're looking at the given of f and g, they already have restricted domains. So start by evaluating that first, just like we did in part A. So let's take a look at f of x and think about the domain for this particular function. Okay. Remember, what do? Set it greater than or equal to 0. Good. So here I'm going to do 4 minus x squared is greater than or equal to 0. I'm going to bring the x squared over. I'm going to take the square root of both sides, and I'm going to get plus minus 2. I have to be careful here. I get solutions of plus minus 2. These are what we call critical values, and it helps by evaluating in a number line so that way you can see where are your solutions on the number line. You know you're including plus minus 2, so that would be closed circles or brackets if I were using interval notation, and we can technically substitute that in here. 4 minus 2 squared, 0. 4 minus negative 2 squared, 0. So those work. I know those are part of the solution. The next thing I want to do is test on the left of these points, in between these points, and to the right of these points, and see where are my solutions. I know my solutions in here. I'm going to go ahead and substitute 0 in here. 4 minus 0, square root of that is possible, so my solution is actually in between here. But just to show you, if I were to pick 3 squared, 4 minus 9 would give me a negative value, then I can't take the square root of that. And the same thing's going to happen if I pick anything to the left. So my domain for this particular square root function is from negative 2 to 2, including those values. So it's very restricted. So when I'm adding, subtracting, multiplying these domains, I have to take this into consideration. We also want to evaluate the domain of this particular square root. So remember, what we're going to do is we're going to take what's on the inside. Because it's not in a fraction, it's just hanging out by itself, we're setting it greater than or equal to 0. X has to be greater than or equal to negative 1. So the domain of this particular function is from negative 1 to positive infinity. Alright, so let's start adding and subtracting these functions together. So let's take f plus g of x. And this is how we're going to write it. 4 minus x squared plus 1 plus x. I cannot do anything further than that. They are not like terms, so we're going to leave them alone. But let's evaluate the domain. Remember, the domain of the first one was from negative 2 to 2, and the domain of the next one was from negative 1 to positive infinity. So the domain of the sum of these two has to satisfy both conditions. It must be that you're from negative 1 to positive 2 only. It has to work in both square roots. So I'm going to evaluate back here what is in both of these. That is my new domain. Okay, so now we're going to subtract them. So we're going to do f minus g of x. And notice that it's identical, except I have a minus sign. Therefore, the domain is the same as what we evaluated for the first part. So the domain is from negative 1 to 2, including both of these, so brackets. Let's multiply them. F times g of x. So now I'm going to have 4 minus x squared times 1 plus x. Both of these can technically come under the radical together. And let's just leave it like this. 4 minus x squared times 1 plus x. The domain is the same thing as before. As the first part, let's call this A. B, and C because of the same reason. Okay, so our domain is still from -1 to 2, including both of these values. Okay, now we're going to divide these two together, so f divided by g of x. We're going to take f of x, that's our numerator, so 4 minus x squared, and then g of x is our denominator, 1 plus x. Now you cannot equal -1. Before you were allowed to equal it. Now you cannot equal it because if you substitute -1 into the denominator, it's undefined. Therefore, the domain now is parenthesis -1 to 2. Alright, let's take a look at this example. Here we're going to find f of g and g of f, and we're going to find the domain of each function, of each composite function. Okay. So remember, when I'm looking for f of g, I'm just going to plug in g into wherever x is, 1 over x plus 3. However, if we look at f of x, it already has a restricted domain. X cannot equal 0. So my interval notation would be -infinity to 0, union 0 to positive infinity. There's no restriction here for g of x, that's just -infinity to positive infinity. So when I look at my new function, my composite function, do you see that x cannot equal -3? Now you have two restrictions, what you had from f and what you get from the composite. So you cannot have 0 now, and you cannot have -3. So your new domain here, if we're using interval notation, -infinity to -3, union, -3 to 0, union 0 to positive infinity. Again, because x here cannot equal -3, and from the original x cannot equal 0. So you have to consider both. Okay, now let's find g of f. So g of f of x. Now we're going to substitute 1 over x, and we get 1 over x plus 3. So I substitute this into where x is, so that's substituting here, 1 over x, and then plus 3. Your only restriction is x cannot equal 0 here, so it's just like f of x for the domain. Your domain for this one is from -infinity to 0, union 0 to positive infinity. Okay, in this example, there's a couple ways to approach this. When it's written like this, you want to start by substituting -1 into g. So we're going to go ahead and do that, and that's going to be g of -1 is equal to 4 minus -1 squared. So that's going to be 4 minus 1, we get 3. Whatever I get here, think of that like your parentheses, your grouping symbol first. Now I want f of whatever I got here. So we're going to do f of 3 is equal to, now we're plugging in 3 in for x, so that's 2 times 3 minus 3. So that's going to be 6 minus 3, and our answer is 3. We can do similar here, or I could find g of f of x and then plug in 2. I'll show you both ways. So let's do f of 2, and then whatever I get, I'm going to plug into g. So I'm going to do f of 2 first. So 2 times 2 minus 3, so that's 4 minus 3 is 1. And now I'm going to plug that into g. So that I get 4 minus, let me write that, so g of 1. 4 minus 1 squared, and that's 3. Now I said that you can do g of f of x and then plug in 2. So let's take a look at that. So g of f of x, wherever f is, I'm going to plug in g. So that's going to be 4 minus whatever f of x is, which is 2x minus 3, and we're going to square it. So that's going to give me 4 minus, keep this in grouping symbols because you're subtracting it, and we're going to get 4x squared minus 12x, plus 9. Distribute the negative, we get 4 minus 4x squared plus 12x minus 9. Combine like terms, we're going to get negative 4x squared plus 12x minus 5. And now I want to substitute the 2, because remember we had g of f of 2. So wherever x is, I'm going to substitute a 2, and that looks like this. So negative 4 times 2 squared plus 12 times 2 minus 5. So that's going to be negative 16 plus 24 minus 5. And that gives me 3, which is the same answer as I got before. So you have a couple options for this particular problem. Alright, for this example, what we're going to do is we're going to look at these graphs and we're going to evaluate it. So here, we're going to substitute, we're going to find f of 3 first. And f of 3 is this point here. My output is 2. And then we're going to find g of 3. And if you look over here, g of 3, the output is 1. This problem is telling me to add them together. So I'm going to do 2 plus 3 and we get 1. So for part B, I'm going to do the same thing. I'm going to find f of 2. And f of 2 is corresponding to 0 for the y. And then I'm going to find g of 2. And g of 2 is corresponding to 2 at the y. I want to divide them, so I do 0 over 2. My answer is 0. For the composite, first, remember, we're going to substitute 2 into g, and then whatever we get, we're going to plug into f. So it's easier to think of it this way, f of g of 2. So 2 was giving me an output of 2 because we already evaluated that. So now I'm going to do f of 2 because I did the parentheses first. And f of 2 gave me an output of 0 because that's what I got over here. So my answer here is 0. I'm going to do something similar here. If it helps you, rewrite it like this. So now I'm going to find 2 for f and we get 0. So now I'm going to do g of 0. And at 0 on g, our output is 4. Okay. Example 5 says find two functions f and g such that f of g of x is equal to h of x. What you're going to do in this problem is you're going to break up h of x. I like to break it up into the two easiest functions that I can think of, that when I plug one into the other, I end up with this. I like to always make f of x the parent function. So I want you to think about this of the parent without the transformation. So that's going to be f of x is equal to x squared. G of x has to be everything else. So what did you plug into x in order to end up with h squared? Well, that's going to be what's inside the parentheses. So your answer is going to be 2x plus 1.